This video is going to be discussing some extra sort of concepts in practice with velocity versus time, because I think the normal materials don't hit that as hard as I would like. So I'm going to quickly go through these few problems here using velocity versus time graphs. So the first thing, this task has us go through and rank these according to distance traveled and displacements. And so when we do that and we're looking at velocity versus time graphs, what we're going to be doing is finding some areas here, and it's the area between the velocity versus time graph and the axis. And so I imagine it creates these little boxes here, like, for instance, there's a box like right here, and there's another box like right here. All right, and we're going to find the area of these boxes, and that will help us figure out what the distance traveled and the displacement are. So this first box here is a 2 by 4 box, if you look at the different axes, which means that it has an area of 8. And then the second one here is a 2 by 4 box, but going the other way. So it's 2 meters per second, but for 4 seconds. And so that also has an area of 8. Looking at these then, what we can do is we can determine the total distance traveled. You just add them up, 8 meters plus 8 meters. So for this one, I would say distance equals 16 meters, and the displacement is going to equal, for this one, we look at, some of this is below the graph, the axis, some of it has negative velocity and some of it has positive velocity. So this right here, that's negative, all right, negative velocity. This part here, this is positive velocity, positive area, and so that's going to add it's going to add to where our position is. And so because we've got sort of like 8 meters where we're going in the negative direction and 8 meters where we're going in the positive direction, they end up canceling each other out. So we call this, it'd be 0. 8 minus 8 is 0. 0 meters. All right, so that's how that one works out. For the second one, we're going to do the same sort of thing. I see 3 sort of areas here. We got 1 here, we've got 1 in this region here, and we've got 1 here, and so we're going to find this. Only this last one is below the axis. It has a negative velocity, so that last one is going to be negative. The other 2 are going to be positive. All right, so when we look at this, finding the area, the first one here is 4 by 2, so that's going to make it 8 meters. This next part is 2 by 2, so that's just 4 meters here. All right, and then the other one is 2 by 2 as well. It's 4 meters, but it's 4 meters below. So if we look at the distance traveled here, you just add them all up. Again, for distance traveled, there are no negatives because it's like your odometer reading in your car. It's just going to keep going up as you're moving around. It's not like it backtracks, like it goes down when you backtrack. So for our distance traveled here, you just add those all up. The distance traveled equals 16 meters. For the displacement, though, the change in position, we have to take the ones that are positive and subtract away the ones that are negative. The first 2 sections there, the 8 and that first 4, the ones that are above the axis, those are positive, so that adds to 12. But then we subtract 4 because there's the 4 meters below the axis that's going in the negative direction. And so 8 plus 4 minus 4, that ends up just giving you 8 meters. Alrighty. For this next one, there are kind of just 2 regions here because if the velocity is 0, we're not going to be going anywhere. So we've got this region here, which is above the axis, which means that it's going to be positive, and we've got this region here, which is below the axis. This is going to be negative. This area is 2 by 4, so it's going to be 8 meters. This area here is also 2 by 4, so it's also going to be 8 meters. So if we look here then, our distance traveled is once again 16. Distance traveled equals 16. our change in position is going to be equal to, there was one above the axis and one below the axis, so it's 8 minus 8, which gives you 0 for the displacement. Continuing on down here, we've got three sort of regions here. We've got this box here, and then we've got a little box here, and then we've got a big box here. These are all underneath the curve, so they're all negative. If you're talking in terms of displacement, the object is going in the negative direction the entire time. If you're talking distance traveled, of course, everything's positive. So the first area there, it's a 3 by 4, so that means it travels 12. The second area, it's just a 1 by 2, so that means it's only 2 here. And then the third area is a 2 by 4, which makes it 8. That means if we add all these up, the distance traveled here is going to equal 22 meters. The displacement, though, since all of those are on the bottom, all of those are negative, is negative 22 meters. All right, two more here. On the next one, if you look at this little sort of boxy area here, there's one area, there's another area here. All right, so to calculate the distance traveled and the displacement for those, these are also both negative, so they're both going to be below the axis. The first one is a 2 by 2, so that makes 4 meters there. The next one is a 3 by 4, so that makes it a 12 meter section here. All right, so for the distance traveled on this one, you just add them up. Distance traveled equals 16. For the displacement, both of these are negative, both of them are below it, so the displacement equals negative 16. Last one here, these are both positive. We've got kind of this region here that we're looking at, and then this region here, trying to find the area of those two. This box is a 4 by 2 box, which makes it have 8. All right, and then the last box is just a 2 by 2, so that makes it 4 meters. All right, if we add them together here for distance traveled, we get 12 meters. And then for the displacement, 8 plus 4 is 12 as well. All right, so both of those are positive, so displacement is 12 meters as well. Now we need to rank them from highest to largest, rank highest to lowest, or most positive to most negative. For the distance traveled, notice here there are actually 3 that went 16, 1 went 22, and 1 went 12. So D went the furthest at 22. And then A, B, C, and E all were the same, so we just put equal signs in there between them. And then F was the lowest there with 12. A, B, C, and E could have gone in any order. I just put them in alphabetical order, but because they're all equivalent, it doesn't matter where they are as long as you specify that they're equivalent. For the displacement, we're looking for the most positive here. It looks like we have a 12, an 8, 2 zeros, a negative 16, and a negative 22. So the order here then for that would be F, because that's the 12. The 8 is B, and then C and A are equal, so B and then A equals C. Those are both 0. And then we've got the negative ones here. E is negative 16, and D is negative 22, so we'll have E and then D. Alrighty, so that's how that works for the ranking tasks and how you find displacement and the total distance traveled given a velocity versus time graph. We'll use that a little bit here on this next page. So this one is telling you to make some different things based on the velocity versus time graph, and we're going to use the same general principle here as we used on the back. And so you're given a velocity versus time graph. You can look at the areas here. So for instance, there's an area here, and then there's another sort of box right here, and there's another sort of box here. And you can use that to figure out what the displacement is in specific parts of the graph, and that will help you figure out how to graph it. So for the instance, this first one is a 1 by 3, so it's sort of got 3 meters here. The second box is a 1 by 2. This one going 1 second and -2. So this one here is 2 there, 2 meters. And then on the bottom here, we've got a 2 by 4, which makes it 8 meters. And so if we're thinking about what happens here, we've got an object and it increases its position 3 meters in 3 seconds, or it's going 1 meter per second as it says, and then it goes down 2 meters in the next 1 second, and then it goes down 8 meters in the next 2 seconds, is what we see there. And so this can help with graphing. I said assume the initial position is 8. So we're going to start here. We'll call this 8. It's going to go up 3. So I'll call this 11 here. And that's going to take it 3 seconds. We have a total of 6 seconds, so I'll just try and 1, 2, 3, 4, 5, 6. Do that. So after 3 seconds, according to the velocity versus time graph, it's gone up by 3 meters, so we'll go here. All right, and then it goes down 2 meters in the next 1 second, so it ends up at 10 in the next 1 second. And then after that, it's going to go down 8 meters in the next 2 seconds. That would put it at 1. So then I just connect the dots. All right, so here, and then it's going down slightly faster than it went up, and then it drops down very quickly. All right. The motion map, always a little bit easier to show what's going on a motion map. So we'll start off here at 8 as well. I'm going to go ahead and put 0 here so that we can get some pretty high numbers. So this would be 5 here, 10. All right, so we know that this object starts at 8. And then it goes up 1 meter per second for the first 3 seconds until it gets to 11. So that's there. All right, and then it's going to quickly change direction. So I'm going to get rid of that dot there and drop it below. It travels with -2 meters per second for 1 second. That brings it back here. And then it's going to go with -4 meters per second for the next 2 seconds. For these ones, these two are the same, and then these first 3 are all the same. All right, but that one oddball one is a little bit of a different velocity there, so it doesn't get a tick mark. All right, so that's what the motion map looks like for that. Going on, we have a second example here. This one just has 2 boxes that we're worried about. This one here, and this one here. The other one, for the other velocity, it's at rest. So it's not going anywhere in that section. So we calculate the area of these. This first one is a 6 by 1 box, so it's just 6 meters there in the first 1 second. The next one is a 3 by 2 box, so it goes down 6 meters here in the next 3 seconds, and then it's at rest. It says assume an initial position of 0. So on this one, what we'll have is it's going to go up. Starts at 0, all right, and then by the first second, and I'll just trace in my 6 seconds here, 1, 2, 3, 4, 5, 6. After 1 second, it's up at 6. Here, up at 6. All right, and then over the next 3 seconds, it falls back down to 0. So it's going to get back to 0 here because it goes down 6. All right, and then it's going to be at rest for the next 2 seconds. For the motion map, I'll just put 0 here. We're going to start at 0. It goes up to 6 in the first second. Okay, and then it's going to abruptly change direction. So I'll have this arrow here, but I'm actually going to get rid of that dot and drop it below because it will abruptly change direction here. And then it's going to go negative 2 meters per second, 3 seconds. And then it stops for 2 seconds. All right, and then we're done. So on this one, the last dot, remember, it never gets an arrow on it. So count the number of dots, though. We've got 6 seconds. We should have 7 dots. And that checks out. So this is what that one looks like. A little bit confusing, but hopefully not too bad. All right, so that is that with the velocity versus time graphs. If you have any questions on that, make sure you come in and see me.